We're going to talk about now finding high points, low points on a graph. So let's just start off with something simple. We've got f of x equals x squared minus 2x. Now what we're going to be looking at, we're going to focus on multidimensional or multivariable functions, functions with two independent variables. But we need to go back and think about the functions with one independent variable like this one. Now, in finding the high point or low point on graphs like this was something we probably started doing back in Algebra 2, where we recognize this is a parabola and we want to find the vertex. And one of the ways that we can find the vertex is by completing the square. So we might have done an exercise like this. We take the x squared minus 2x, take half of that negative 2, square it, and you add a 1. But I can't just add a 1 without subtracting it off. I mess up the balance. So then what we have is f of x equals x minus 1 squared minus 1. And this tells us that the vertex is 1, negative 1. And in fact, you know, if you look at the graph, that's exactly what you get. You see right here, this x value of 1 gives you a minimum value of negative 1. Now remember what that means. That means when we say that a minimum occurs when x equals 1, that means if we pick any values around 1, let's suppose we pick an interval 0 to 2. If we pick this interval, we know that f of 1 is less than or equal to, well, it's in this case, it's just less than any other value, f of x, in that whole interval. So you pick any x between 0 and 2, and f of 1, let's make it inclusive, is less than or equal to that. So that's what we mean by minimum. If we were talking about a maximum, we would say f of 1 is greater than or equal to any value in that interval. Any function value taken from x's in that interval. But anyway, here's what we've got. So we found the minimum through just an Algebra 2 method. Now, when we studied calculus and studied the derivative, we said, well, I noticed that at this minimum, the tangent would be horizontal. So this led to us looking at the derivative, because it's the derivative that gives us slopes of tangents. And it looks like to me at this minimum, the slope of the tangent is going to be 0. So I took the first derivative, set it equal to 0, and found x equals 1. And I call this a critical number. Okay. Now, critical numbers can also occur, remember, when the first derivative is undefined. So wherever the derivative is 0 or undefined, we say that's a critical number. So notice then if I plug that 1 back into the original function, I get 1 squared minus 2 times 1, which is negative 1. And so I found that the point 1, negative 1 is the vertex, just like I did here. So that's what we discovered with calculus. Now, we also, while we were studying this, talked about ways to identify whether or not we have a high point or a low point. And we used what's called the first derivative test. So for example, I've got 1 as my critical number. I can pick a number to the left and right, maybe 0 and 2. And I'll just test the function. I'll plug these numbers into my derivative. So I've got 2x minus 2. I'll plug in a 0 and I get negative 2. Now, being negative, that tells me the derivative is negative. That means the function is decreasing. If I plug in a 2, I get 4 minus 2, which is 2. Positive first derivative, so the function is increasing. So what happens is we've got this situation where the function is decreasing until you get to the critical number, and then it's increasing. That indicates that it bottomed out. You have a minimum. Now, if it goes the other way, you have a maximum. We also learned the second derivative test. And, you know, we would take the second derivative. In this case, it's 2. And we said that if you plug in the critical number into the second derivative and you get a negative, that means you have a maximum. If you get a positive, you have a minimum. So that's just some preliminary, and then now we want to build on that. So now we look at a function with two independent variables. F of xy equals something with x's and y's in it. Now we can approach this problem the same way. We could complete the square with this particular one. So I could say this. I could say, okay, f of xy. Group my x's together. Group my y's together. I'm getting ready to complete the square. I take half of this -6 and get -3, square it, and add a 9. But I can't just add a 9 without subtracting a 9. It would be unlawful. If I take half of the 8, I get a 4, square it to get a 16. So I got to subtract off a 16. Now we have this. We have x minus 3 squared for this first part, plus y plus 4 squared for this part, plus 5. And now you can see we could talk about this point right here. Now, this problem was simple because it's a paraboloid, and we notice this is a paraboloid opening up. So when we complete the square this way, we get a 3, a -4, and the maximum value, or the minimum value, is 5. So what we've done is we've located this point. And when we talk about a minimum here, a local minimum, what we're saying is if you have a disk down here, I'm saying this point 3, 4, 3, -4 is I'm saying a minimum occurs there. And what that means is that I can find some disk where 3, -4 is centered, the center of this disk, and every point in there is going to be less than or equal to 5, or greater than or equal to 5. That's what we mean by a minimum. So all the other points around here will give a function value bigger than 5. Therefore, that we say 5 is a minimum then, a local minimum. Now this one is easy because it's a paraboloid, and we know, how to find the vertex of a paraboloid. But not all functions are as nice as this. So what we want to do is we want to find a way that we could perhaps find where a maximum or minimum occurs, knowing very little about the shape of the surface or what kind of surface we're dealing with. Well, if you think about it, let's think about a directional derivative. And remember, we said that a directional derivative we could find by dot producting the gradient with the direction of the derivative. In other words, the vector that tells us which direction of the directional derivative. Well, now this one, of course, is going to be partial with respect to x, u1, partial with respect to y, u2. Now, if you look at this, and let me go to the next slide just to analyze this a little more. If you look at this, here is a maximum. Let me clear some of this out. You've got a maximum up here. You've got a minimum. And here's what it looks like. It looks like right here at the maximum, right here at the minimum, where in single variable calculus we thought of a horizontal tangent, it looks like here we've got a horizontal plane. And if you think about, okay, well, that means that every directional derivative is 0. The slopes of all these tangents are going to be 0. Well, if you think about that, and you know that the directional derivative is going to be this, and you're saying, okay, that's got to be 0, because what I want to do is I want to find a point where all of the directional derivatives are 0. that would seem to indicate that you've got a plane up there. Well, this is not going to happen anytime unless fx equals 0 and f partial with respect to y equals 0. That's the only time you're going to have that. I mean, u1 and u2 are not going to be 0. They're the direction. So, I mean, if both of them were 0, then you would just have, a point. But we're looking for where the partial with respect to x is 0, the partial with respect to y is 0. So when we want to find our critical number, that's what we're going to do. So let's look at this. Let's take the partial with respect to x and see how this works. So we have 2x minus 6. Okay? And then let's take the partial with respect to y. Partial with respect to y is going to be 2y plus 8. And we go ahead and set those both equal to 0. So this one gives us that x is equal to 3. And this one gives us that y is equal to negative 4. So it looks like we're saying that a minimum occurs here at 3, negative 4. And remember, back on the previous slide, that's what we found, 3, negative 4. Now we can plug those numbers back in and find what that minimum is, and we found it to be 5. So with this one, we could see clearly, yeah, this is a paraboloid opening up, and we knew that we were finding the minimum. So whenever we went through this process, we found the x, the y, and we knew that corresponded to a minimum. Now, it won't always correspond to a minimum. Here, notice you have a maximum. Going through this process would give you a point that gave you a maximum. Here, a minimum. Here, notice that this process that we just did there, this derivative, the partials are undefined. So when we talk about critical numbers in single variable calculus, we're saying wherever the first derivative is equal to 0 or undefined. We do the same thing here. Whenever the partials are equal to 0 or undefined, we're going to call that our critical points. Now, you can also, we're going to be talking about saddle points, like here. This is an example of a saddle point where if you look at this point right here and I say, well, is it a high point or a low point? Well, it depends on how you look at it. If you're going this way, just along this curve, it looks like a minimum. But what if you're coming up a different way? So here we have an example of a saddle point. And what we have to be able to do is we have to be able to identify, when we go through this process of setting partials equal to 0, we need to be able to identify what kind of point we locate. So that's what we're going to do now. Okay, so let's look at what we're going to use. Remember, in Cal 1, we have the first derivative test, the second derivative test. Well, here, we're going to have something similar. We've got minima, maxima, and saddle point. We want to be able to identify what kind of point we're dealing with. So we're going to look at the second derivative test for functions of 2 independent variables. And here's what's going to happen. We are going to look at this thing. Let's suppose we've got a function. And here's the way we're going to look at it. We have the second derivative, fxx, fyy. And down here we will, well, let me, I didn't do that right. Let's see here. This might be a way to help you remember it. And then down here is yy and yx. If you look at this little determinant looking thing and you work it out, you notice you get, actually, I did it wrong again there. Sorry about that. Here we go. So it's not very helpful for me. Okay, so if we go, just finding the determinant like usual, and then we have, since f, x, y, and yx are the same, let's just call this squared. This is just a method that you can use to get this formula. But this is the formula that we're going to use to determine whether or not something has a max, min, saddle point, or maybe this test won't always work. But here's what we have. We're going to call this D. And so let me just write it here. Okay. Or YX, it doesn't matter. But here's what we're going to say. We're going to say that if this is, first of all, if this is positive, one of two things has to happen. In other words, if this whole thing is greater than 0, you're either going to have a maximum or a minimum. If it's greater than 0, you're going to have a minimum. If it's less than 0, you're going to have a maximum. It sort of harkens back to the second derivative test, where greater than indicates a minimum, less than indicates a maximum. But notice what you're doing. You're using the fxx, so this one right here. So if this is greater than 0, then it's a minimum. If it's less than 0, it's a maximum, provided this whole thing is greater than 0. Now, if D is less than 0, then you have a saddle point. End of story. If D is equal to 0, then you just have an inconclusive test. So here's the thing. D greater than 0, you have a max or a min. As soon as you discover that D is greater than 0, you go back and you look at fxx. If it's greater than 0, min, less than 0, max. So let's see how we could use this. Let's look at a function. Now I've got the graph of this function here, but let's just go through and see how this would be used. So from the very beginning, here's what we want to do. We want to start off looking at the partials. Okay? So I'm going to have the partial with respect to x. Okay? So here we go. This is going to be x squared minus 2x minus 3. Okay? That's the partial with respect to x. And we're going to set that equal to 0. We're going to take the partial with respect to y. Partial with respect to y is going to be 4y squared minus 4. And that 2 is going to be equal to 0. So we're in the process of trying to find some critical points. So I have this. Now, let me just see what will make this equal to 0. I believe that I can factor this. Okay, so now I'm just solving it like I always, any other quadratic. I'm just focused on that. So maybe this is going to be negative 3 and plus 1. And that would give us that we've got x equals negative 1 or x equals 3. Okay, those are the two x values that are the solution. Now for this one here, if I bring over the 4 and divide by 4, I get y equals plus or minus 1. So this solution is y equals plus or minus 1. So what we're saying is some things happen on this curve, and here's where they happen. Here's what we want to look at. We want to match each x up with each y. So I'm going to start off saying, okay, let's take x. I'm going to say negative 1, comma, 1. I'll look at that. Then I'll take negative 1, comma, negative 1. So what I've done is I've matched up the negative 1 with each y. Now I want to do the same thing for the 3. I'm going to take 3, 1, and 3, negative 1. So that's what I have, 3, negative 1, 3. So I've got 4 points here to consider. Now, I'm going to need the second derivative because what I'm trying to do is use that formula that we just looked at. I'm trying to find big D. So here we go. The second derivative is of, let's see here, second derivative is going to be 2x minus 2. Okay, that's the second derivative. Now let's go ahead and do the second derivative of the y. And that's just going to be 8y. Now let me go ahead and do the f of xy. the f of xy, because we're going to need that one. And the f of xy is going to be 0. Okay? So now what I want to do is go ahead and see if I can use my formula here. So here's what I'm going to do. I'm going to plug in these values into my second derivatives. So let's see what we get here. Now, fxx, so this is going to be 2 times negative 1 minus 2. And of course, minus 0, but there's no point in doing that. Now, this is going to be negative 4. Negative 4 is less than 0. So that tells us that we have a saddle. Because remember, they've got it, if you look back, let's just go back and look at it real quickly. If d is greater than 0, then you have a max or a min. If it's less than 0, then you have a saddle. So that's something you can keep in mind there. Now, let's look at this one here. Oh, by the way, I messed up on this, right? The answer's not wrong, but I forgot the, so I've got 2 times negative 1 minus 2, and then times 8. I forgot the times 8. But still, we get something less than 0, so it's a saddle. Okay, so don't be thrown off by that. This is fxx. This is fyy. See, I put the 1 in for the y. Okay, so don't be thrown off by that, by my mess up. Okay, now let's try this one. This is 2 times negative 1 minus 2 times negative 8. See, so now I put the negative in. So now we have a negative times a negative. That's a positive. Okay, so that tells us we're either going to have a max or a min. Now, you'll notice that fxx of negative 1, that is less than 0. So it looks like we have a max there, local max. Okay, so far we have a saddle and we have a max. Now let's look at this one here. We've got 2 times 3 minus 2, okay, that's positive, times 8 times 1, that's greater than 0. Ah, good. Okay, so now we have a max or a min, and if you notice that fxx of 3, 1, that's greater than 0, so it looks like we have a min. Now let's go this way. So here we have 2 times 3 minus 2 times negative 8. Okay, now that's a positive times a negative. That's less than 0. And since you have something less than 0, you know that that's a saddle. Now to actually get the maximum value, to actually get the minimum value, you would need to plug these points back into the original. So if I actually wanted to find out what the maximum value at negative 1 is, I would plug it back up here into the function. If I wanted to find the minimum value, I'd plug in the 3, 1 back into the function.